Okay, and let me just do it on Panopto as well. Okay, let us continue here. So we can write it exactly as for any point C in the interval, we can say that limit of f of x when x approaches C will be the f of C if C is in the interval. Remember, if we use a parenthesis here, it means C is different from A and B, right? It's larger than A, smaller than B. And especially at the endpoint f of x, when x approaches the right side of A, it should be f of A if it is continuous on this interval. Okay? And the last case, when x approaches B from the left, it will be f of B. These are the endpoints, A and B. Okay? So we know the definition of it already. And now there are some theorems. We just have to accept that. You can read this on the book, or here. It says that if f and g are continuous, at x equal to a, and c is a constant, okay? The following functions are continuous. First, the sum or the addition or subtraction of the two continuous functions is still continuous. Okay, that is the first properties, plus or minus. The second property is, if f is continuous at A, g is continuous at A, then their product will also be continuous. Okay, it means lambda exists. 3, the quotient of this is also continuous, and we require that g should not be 0, because if it's 0, it's not defined. And the fourth one, if c is a constant, cf is also a continuous function. Okay, it's not too difficult. So just memorize them. Another theorem. Remember, the following types of function are continuous. at every number. In their very important things domain. So first, that is polynomial. It has a form of x squared, x to the n in general, x to the ax to the n plus b. Let's just pick one example. You know what it is. Blah, blah, blah. Because polynomial is continuous all on R from negative infinity to infinity. So just memorize them. Two rational function. Example, x plus 1 and x minus 1. What is the domain of this function? In order to find the domain, we need to find the points where it is undefined, right? It is undefined if the denominator is equal to 0, which means when x is equal to 1, then we remove that point. Then any point different from 1 would be in this domain. Or you can write it in intervals terms, negative infinity to 1, union with 1 and positive infinity. They're the same thing, right? Three, root function. Root function, for example, square root of x plus a. It is defined when the things under the radical sign is defined. In this case, x plus 8 should be positive, right? It means x should be larger or equal to negative 8. So the domain of this would be any point from negative 8 to infinity, right? We are allowed to pick negative 8, so we use bracket here. And infinity here we use parentheses because it does not belong to R, okay? So it means that this function is continuous on this domain. 4, the trigonometric function which are sine x or cosine x or tan x, etc. Remember, tan of x, it is defined when tan is sine over cosine. So it is defined. Let me just write it down. It is defined when cosine of x is not 0, right? And if you remember, this is the unit circle we mentioned yesterday. This is cosine, right? This is number 1. This is negative 1. Cosine is different from 0. It means that we are not allowed to pick the point where the angle is right here. or right here, right? It is pi over 2 or pi over 2 plus pi, so on, whatever, yeah. Review that. We're not going to that much detail here because you know that before already. So the inverse of trig function. Which are sine inverse or cosine inverse or tan inverse. Review the domain of these. Read the book. And another type is exponential function. Which could be e to the x, e to the 2x, or whatever. Okay? Or the log function. Which is natural log of x. In this case, the domain of this natural log, then x should be positive, right? Okay, remember all these properties and let us take a look at this example. Okay. Now, in this example, where are each of the following function discontinuous? Discontinuous, remember the definition, right? So they ask us, the first one is the function f of x is x squared minus x minus 2 divided by x minus 2. That is the first function. And another function, g of x, defined as x squared minus x minus 2 divided by x minus 2 when x is not 2 and it is 1 at x is equal to 2. The third function which is 1 over x squared if x is not 0 and it is 1 if x is equal to to 0 right here. Okay, this is the question. Now we need to solve this one. We don't have to make a graph of this, but for your information, let us just look at the graph here. This is g of x, h of x, f of x, I'm sorry. And c be like this. And at 0, it is 1. Okay? And the function g of x at 1, it will be 2. There's only one thing different. At 2, it is 1. And g of x is also identical to this guy. And you get that right. Because if I draw it, it makes it worse. Now you see it. Okay, now when we solve this one, the function f of x, let me just rewrite it here so that we can all see it together. What we need to do is to find the domain of this first, right? And see where it is defined. So it is defined when this guy is not 0. So the domain will be x is not 2. Or we can write it from negative infinity to 2, and then union with 2 and infinity. Okay? Because f of x is not defined at x is equal to 2. Therefore, f is not continuous at this point, right? That is one thing. It is not defined, then it is not continuous.
How come you don't factor the numerator?
Yeah, we can do that, but for now we just observe that and we see it immediately. At x is equal to 2, then it is not defined because at x is equal to 2, the denominator is 0, right? We cannot write a number something over 0. It is not defined. We are not allowed to do so. Because it is not defined, then it is not continuous. Okay? Because from definition, a continuous function, it should be defined at that point, right? Here. We mentioned that yesterday. Here. First, it should be defined at that point. Then limit of this should exist, and the limit should be the evaluation of this at that point. But it's not true. This example does not satisfy the first condition already. So we can say that, okay, it is not continuous at this point, or it is discontinuous at this point. Okay? We don't have to do anything more. You can say it immediately. Now, let us continue, let us solve B. Okay? B is exactly the same function, but there's one more range at x is equal to 2. That is the only difference. we see that it is defined at 2, right? Here, right here. So g of x is defined at x is equal to 2. So the first condition is satisfied. Then we consider the next one. We need to find whether the limit exists or not, right? It means at this point, we need to find the limit of x squared minus x minus 2 and x minus 2 here when x approaches 2, and see if we can find a limit of this. Again, like you suggest, now we can do it. The limit of this when x approaches 2, the numerator is x minus something here or plus times x minus or plus something here. And what are these two numbers?
1 and 2.
Very good. 1 and 2 here. We can file it to double check it, right? Very good. Now we see that the numerator and denominator, we can cancel each other. And this becomes much easier. Now it becomes limit when x approaches 2 of x minus 1. Oh, yeah, plus 1. Very good. Thank you. Plus 1. So this is a polynomial of degree 1 or a linear function. As we have mentioned before, this polynomial is continuous everywhere in the domain. It means that we can substitute the value of x is equal to 2 here. It is continuous all over the domain, therefore it is continuous at 2, right? It means that we are allowed to substitute this value. To here it becomes 2 plus 1, which is 3, right? So we found that, okay, limit of this is equals to 3. But what is g of 2? Yeah, we are given here, right? We are given here. G of 2 will be 1. We are given. So it is 1. Oops. We see that limit of g of x when x approaches 2 is equal to 3, which is different from 1, and 1 is g of 2, right? So this violates the third condition of continuous, right? Remark. But we say that it is not continuous. Because if it is continuous, then g of 2 should be 3. These two values should be the same. So it is discontinuous or not continuous at this point, right? Very good. And here is the graph of it. We see that when we draw the function g of x, it is this line, and this point here, we need to remove the pen from the paper and continue drawing this and make a dot here at x is equal to 2, which is discontinuous, right? So in the example C, let us see. In the C, the function h of x is defined as 1 over x squared when x is not 0, and it is 1 when x is equal to 0. We see that h of 0 is 1. right? Which is, it is defined. So again, it is defined, then we need to find the limit of this, right? Now let us take a limit of h of x when x approaches 0, but not equal to 0, which is limit of 1 over x squared when x approaches 0, right? And we see that when it comes closer to 0, it becomes a very big number. Or we write it, does not exist or equal to infinity here. So therefore, the limit of this does not exist, then it is not continuous, right? Or discontinuous. At x is equal to 0. Okay. So we call these points this point okay. This point at here, the function f of x is discontinuous as x is equal to 2. This point. And this point, we can remove it, right? If, okay, now look at the g function. The g function here is x squared minus x minus 2 divided by x minus 2 when x is not 2 and x is equal to 2. We know that limit of g of x when x approaches 2 is from this. We have no, it is 3, right? And now, if we defined this point at x is equal to 2, right? If we define the value here is 3, if we define this way, it is now the function, it means that we fill the hole right here, right? Fill up it by a number right here. Then it becomes a continuous function. Okay? So this discontinuous point, we call it removable discontinuous because we can remove it and it becomes a continuous point. And here, the second case in C, it is infinity discontinuous. Just make sure that I'm finding the correct names of it. Infinite discontinuity, okay? So we have some names for them. The first one is removable discontinuity. Is in A. And the second one, the infinite discontinuity. As in the previous example in C, right? And there are some other types. We call it jump discontinuity. So for this one, let us take a look at the example, the floor function. It is defined as like this. It will round up the number to the nearest integer below that point. Wait. No. The charger. Oh, sorry about that. Let me try. Hold on, wait me a second. I will close all the application because my computer is run down of battery. Sorry, my bad. I still see it. Can you still see it? Okay, this floor function is defined like this. Then it will return for example, at x is equal to 1.9, then f of x will be the smaller number, right? Integer, which is 1 in this case. How about at x is equal to 2.001? This function will return the value 2, the lower in the integer, which is lower than the value here. And the graph of this function is like this. At 1, at 1 for any value larger than 1, it will be 1, right? And for any value of x from 2 to 3, smaller than 3, the value will be the same, will be 2. And here is this. And 3 will be here, like this. So on and so forth. We call it the jump discontinuity, right? When we draw the graph of this, we need to take our handoffs out of the paper and continue. So, for the removable discontinuity, it is easy to make it continuous at this point by filling the gap by the limit of the function here, right? And now, evaluate the function. So that is all new concepts. consider this. Evaluate the function, the limit of sine x over cosine of x. Let me say 2 plus cosine of x for now. It's better. When x approaches pi, right, using the continuity, we see that the trig function sine x is continuous, right? From the previous theorem. And cosine function is also continuous at this point. Hold on a little bit. Excuse me. To ensure that everything will be okay, let me log into my iPad. Hey, welcome me. Okay, then the cosine function is continuous. All over R, right? Or we say that from negative infinity to infinity. And the same thing. Sorry about that. And we see that the cosine function is always larger than -1 and smaller than 1. Sorry about this issue. I didn't expect that. Or any of you have a charger of MacBook? Okay. Or let me just talk about this, and then the next day I will continue, right? So first, the function here, cosine is always larger than -1, smaller than 1. Then 2 plus that cosine function, it will be always larger than 1 and smaller than 3, right? It means the function here is always defined, right? So then at x is equal to pi, we're good. It is continuous at that point, right? Because it is continuous at this point, so we can evaluate the limit of this by plugging the pi to this function. And then the limit will be simply sine of pi divided by 2 plus cosine of pi. We see that sine of pi will be from the unit circle. Sine of pi is 1. Sine of pi is 0. And at that point, cosine of pi will be -1. So this function becomes 0 divided by 2 plus -1. It means 0 divided by 1 and simply becomes 0, right? I think we can stop for today and see you tomorrow. You have a good one. See you at the office hour. Please join and introduce yourself. Thank you. See you.
I think that you marked me absent whenever you were doing the.
Can you write me an email? For now, my computer is running out of battery. Yeah. Thank you.
And I'll email you about the Moodle or the website thing.
Yes. Yes.
Thank you.
You're welcome. See you then.